Gravity. You know it's real every time you trip and fall, drop your keys, or watch a ball arc gracefully through the air. Gravity pins us to Earth's surface, causes the tides, and holds the entire solar system together. And yet, when you look closer, gravity seems to have a strange double identity. It's both unimaginably powerful and shockingly feeble at the same time. Let's start small. Pick up a paperclip, hold it in the air, and let go. Instantly, Earth's gravity grabs it. Pulling it down seems strong enough, right? But now, hold that same paperclip just above a small fridge magnet. The magnet wins every single time. The feeble little magnetic force from a dollar store fridge magnet easily overcomes the pull of the entire planet Earth below. So, how is gravity, the force that steers planets and galaxies, so easily beaten at your kitchen table? To start answering that, let's look at the four fundamental forces of nature: electromagnetism, and the strong and weak nuclear forces. Each has a different job. The strong nuclear force binds protons and neutrons in an atom's nucleus. It's extremely powerful, but it works only at subatomic scales. The weak force is responsible for radioactive decay and also acts at tiny distances. Electromagnetism, the force behind light, electricity, and magnetism, is strong and acts over long distances. And then there's gravity, the oddball of the group. Gravity, as we experience it, is by far the weakest of the four forces. Consider two protons. The repulsive electric force between them is about 1036 times stronger than their mutual gravitational attraction. That's a 1 followed by 36 zeros. If gravity were just a bit weaker, stars couldn't form. If it were much stronger, the universe would collapse in on itself. So why do we ever notice gravity's pull at all? It turns out gravity has one big advantage: it never turns off. Electromagnetic forces can attract or repel, and charges can cancel each other out. Think of how a positive and a negative charge neutralize. The same goes for the nuclear forces. They have tight boundaries in space and don't work outside the atomic nucleus. But gravity is always attractive, and every bit of mass in the universe adds up. There's no negative mass to cancel it out. The result, in everyday life, gravity may be the weakest force, but on huge scales, planets, stars, galaxies, it becomes king. Every atom in your body is being pulled by every other atom in the planet beneath you, and all that adds together to give you weight. Let's zoom out, look at Earth and the Sun. The gravitational pull between them is what keeps Earth locked in its orbit for billions of years. Go bigger. The Sun orbits the center of the Milky Way, drawn by the gravity of 100 billion stars. Structures like galaxies and clusters of galaxies are bound by gravity alone. None of the other forces get a say beyond their tiny native scales. But why is gravity so comparatively weak? This is one of the big mysteries of modern physics, sometimes called the hierarchy problem. There are ideas, but no definitive answer. One idea is that gravity isn't actually weak. It just leaks into extra dimensions beyond the familiar three of space and one of time. We see only a diluted version in our 3D world. Another idea is that the particles that transmit gravity, called interact differently than the particles for the other forces. But while physicists have explored these ideas, solid experimental evidence remains elusive. What we do know is that the weakness of gravity gives us a universe with just the right conditions for complexity and life. Stars burn slowly and steadily. Planets can have atmospheres. The cosmos doesn't crush itself, nor does it fly apart. So the next time you watch an apple fall from a tree echoing Newton's legendary epiphany, or feel your feet pressing into the ground, Remember that you're witnessing the weakest known force in physics, and yet, without it, there'd be no stars, no planets, no you, and no me. Gravity's contradiction so weak, it can't hold up a paperclip, yet so powerful, it binds the universe isn't just a quirk. It's one of the deepest, most fascinating puzzles we can observe, hinting that even in what seems ordinary, there's a whole universe of mystery still to be uncovered.